And then of course, now what more you gain out of it? What you gain is the following. If you take equation eta, then this has any eta in Q plus. That means given eta, there exists a sign such that psi into psi is equal to eta, which you designate by, then you designate psi is defined as square root of eta. See, so it's a game. This is where we were stuck there actually. Okay? And this is true for every eta. For any eta. Whereas this was not true when we were considering simply Q plus. For example, you have seen that the equation x square equal to 2 does not have a solution. So that's the structure of something. Now we designate this as follows. So one more thing that I want to say is that all the natural numbers can be certainly obtained as a cut. What is that cut? The cut is this. See, psi equal to the set of all x belonging to Q plus such that x is less than n. This is what we call n. So all the natural numbers are embedded in this collection of cuts. All the rational numbers are embedded in the collection of cuts. So what have we obtained? What we have obtained is this following structure. You have n on one side. So this is not equal to, but you got something more than this. Then you got this is a collection of ordinates. So every natural number can be considered as a cut. Every rational number can be considered as a cut. Okay? Therefore, you have this natural embedding of n in Q plus and Q plus in R plus. So that's the wonderful thing about it. And you see that the addition, multiplication and order is exactly a extension of the corresponding properties that you had for n and Q minus. But we get a lot more here because you see that all the quadratic, all the what you call equations of the type psi square equal to eta always has a solution for any given. So that is the extra gain that we have obtained. In fact, what one can prove is that this actually fills the gap. Okay, so one can prove that. Okay, let me just say the following. So you take all bounded sets. So you consider so let A be such that there exists n M positive such that X is less than M for every X belonging to Q. Then you say A is bounded. The boundary. What one can prove that A has a least upper bound. Upper bound. What does it mean? Suppose this is your and this is bounded by 1. Now you see this is just one bound and there are several bounds. So out of all the bounds, you choose the smallest. Okay? Out of all the upper bounds, you choose the smallest. Least upper. And what you can show is that there exists an element of R plus, which is the least upper bound. So every bounded subset of R bounded above has a least upper bound. Now this is the so-called least upper bound property. And this is you go for the extension of Q plus to R plus using the least upper bound property. You say that there exists such a set. And there is another way of achieving this. This is also through a very interesting restriction. Take all Cauchy sequences made out of this and then show that. See, the problem with Q plus is that, you see, you cannot ensure that all Cauchy sequences converge. What do you mean by that? Suppose you have a sequence of points Xn with the property that Xn can be made arbitrarily small by choosing n. Suppose you have done maybe some analysis. Consider such sequence, or what you call convertible sequences. Okay. Now the question is, does it converge? Does it converge in R plus? What you can prove is that all Cauchy sequences converge in R plus. Okay. And what more you can prove? Yeah. Whereas in Q plus, it doesn't. You cannot make the same statement. Why? Because if you look at, E does not belong to. Just giving a simple example. What is E? E is the infinite series. So you can get a sequence. Construct now. What is the sequence? So you take the sequence of 1, 2, 2 plus 1 by 2 factorial, comma, etc. 2 plus 1 by okay, etc. So you have the general term coming as sigma 1 by k factorial, k running from 0 to n. So this is the general term and so on. So you get this sequence. This sequence, they are all sequence, all the elements of this sequence are k equal to 0 to n 1 upon k factorial belongs to 2 plus. So no problem. But does it converge to an element in 2 plus? It doesn't. That's the problem. And we know that this is the limit is e, exponential number, and e is not rational. So such numbers have been captured. You can capture it through the insistence that all Cauchy sequences of rational numbers converge. So you embed Q plus in a larger class of objects with the property that in the larger class all Cauchy sequences of rational numbers do converge. Okay? Then such a larger class is again called R plus. Okay? So that's how the construction. There are many ways you can achieve this. Okay. Right. So that in a way completes the construction of R plus. Right? So still, you know, all those things hold, namely that there is no smallest element in R plus. Okay, we said something of that sort here. That does not exist a smallest rational number. There does not exist a smallest real number or element of R plus, because if you have an element of R plus, then it's that number. See, this is an element of R plus. When you see psi by 2 is certainly less than psi, so that is. Further, you can also prove that the Archimedean properties. That is, given psi eta belonging to R plus, there exists an n belonging to n such that eta is less than n times. So this is the which is the extension of the same property that you have on this. That you can see. This is a lot of work involved if you want to really do this. And, you know, several lectures are required, as I was telling. But I am just giving you a feel of what exactly R plus is. So we have successfully pegged the holes. Okay. Now we have successfully pegged the holes. There are no holes there. In fact, it so happens that you can show that there are more irrationals, for what you call irrationals, non-rationals, than rationals. Okay, so that you would have seen working the cardinality of these sets. You can show that the cardinality of Q plus is LF naught, whereas that of R plus is C. C is in fact, this is a symbol into the power LF naught. So this is certainly the continuum. That's why C is used. And you have LF naught. LF naught is cardinality less than that of C. So that is something about it. So after constructing Q plus, you are seeing that this line is full of holes, and there are more holes there than the filled up regions, although deceptively it is not visible. Now this is something what I said initially, that when we go when we transcend from say the natural numbers to rationals, you start observing very weird new phenomena. Like the nextness was the first casualty that you had. Okay, the concept of nextness really withered away. Then we found that there are a lot of gaps. Now we are able to fill the gaps also. So certainly here the gaps have been very satisfactorily filled. So you have a sort of continuous line that you have, and you see that once again you don't have any discrete structure. See? It's a rather smooth flow that you have here. Okay. So this is actually the model of time flow. Suppose you take this as the 0th time, the time from which we are going to start. Then whatever time that is to come, it has been already captured by us. So we have completely accounted for the future time. Now we have to capture the past. How to capture the past? Now this is the problem. So we have to go for further extension. Now you see the art is very simple. Okay. So we got 1/2 line, and now simply reflect it. You simply reflect it so that you get the other half of the line. So what have you gained? Let us see. Let us go to our schematic diagram. You have started with N. You have the addition, multiplication, and order. All the structures are there. See, both A plus X equal to B, AX equal to B did not have solution. Sometimes it had a solution, sometimes it did not have. Then what we did was, we extended to what is called Q plus. With Q plus, so you had here the concept of nextness. This was constructed using piano science. Then we extended this to Q plus. What we did was we looked at the fractions. We went to n cross n, defined a equivalence relation, using that equivalence relation, we got several new objects. And we could also rediscover these natural numbers within that. That was possible. So this was embedded in Q plus. We could extend addition, multiplication and order structure consistently to Q plus. So you had plus, yes, that all this extended. And then you had looked at this equation a plus x equal to b. Still, this equation did not have a solution in all circumstances. It was conditional. Whereas conditional solvable. Whereas if you look at this equation, ax equal to b with a belonging to q plus b belonging to q plus, it's had a solution. That gave q plus a multiplicative group structure. So this is a multiplicative group structure with the order relation and everything. But we lost so this is the summary of what we achieved. Then of course what we did was we extended it further, introducing cuts. We got R plus. Got R plus. And what is the situation? See again you could extend plus satisfactorily. No nextness. And again this equation a plus x equal to b could be solved only conditionally. But ax equal to b always had a solution. And this is also an Archimedean. It's an Archimedean. This is also Archimedean. So again Archimedean. So both are Archimedeans. Okay? But we had one additional property that this accounted for. So equations like x square equal to what do you call it? And psi square equal to x, or what you call p square equal to q, not necessarily has a solution. This was a problem. This did not have a solution. Whereas here it could have a solution. Not only that, this had the completeness property. Except at one end. So I don't want to write that. I will come to this later. But at least there are no gaps. No more holes on the half length. Let me put it that way. Later we will give a more sophisticated terminology for that. Okay? So I think that's a nice place to stop today. And now what I want to do is to build up the whole of R, and they are also building up the whole of Q, and then extending n to Z. Okay, Z is what are called the set of all integers. So in the next lecture I will consider this one, integers, rational numbers, rationals, not positive rationals, and what are called reals. So we had n natural numbers. We denote by, or we call Q plus, give a name, positive rationals, R plus positive reals. Positive rationals and positive reals. Now we still don't have not brought in 0. So our next task will be to bring in 0 and all the negative numbers, and then build what is called R, N and Q. So this is our aim. So we are aiming at construction of R, that is Q and set of integers, set of rationals, set of reals. So we'll take up the construction next time. Okay. Thank you very much.